Okay, for Unit 1, Day 4, we're going to be looking at applications of the slope of the tangent, which would certainly include velocity as an instantaneous rate of change. So let's have a look at this equation about a pebble being dropped off a cliff. I figured that was better than dropping your brother. So our distance, S standing for scalar, is S at t equals 80 subtract 5t squared. So we have a quadratic relationship where 80 is our initial height. So we're going to fill out this table of values. Work with me here. At t is 0, we've got 80. When t is 1, we have 80 subtract 5. When t is 2, we have 80 subtract 20. When t is 3, I've got 80 subtract 45. And when t is 4, I've got 80 subtract 5 times 16, which is 80, so I have 0. So I have a table of values. I just checked it on Desmos. So Desmos is wonderful. You can use it or a graphing calculator to just keep an eye on things. That is not as easy to see as I was hoping. Let's see if I can move it. So we have our initial value of 80, we have this quadratic relationship, and we're going to be talking about the instantaneous rate of change and the average rate of change. So number 2, determine the average velocity of the pebble over each interval. So my velocity is meters per second. So I've got that change in s over a change in t. So I'm going to be looking at the interval from 0 to 1, from 1 to 2, 2 to 3, and 3 to 4, and see that change in velocity. So from 0 to 1, we have gone down 5 meters in 1 second. So 5 meters per second. From the interval from 1 to 2, we've gone down 15 meters in a second. From 2 to 3, we've gone down 25 meters in a second. And from 3 to 4, we've gone 35 meters per second. And then we're done. So from yesterday, we're going to use limits to determine the instantaneous velocity at t equals 1. So we are looking at the limit. So the instantaneous velocity would be the limit as h approaches 0 for the function at 1 plus h, subtract the value of the function at 1 all over h. Here we go. The limit as h approaches 0 for 80, subtract 5, 1 plus h squared, subtract the value of the function at 1. Well, we already have a value for that, so instead of writing out the equation, I'm just going to my chart and say, oh yeah, that was 75, because I have that point 175. Okay, all over h. If I were to put a value of 0 in for h right now, I would have 80 subtract 5 times 1 squared, subtract 75, which would be 0, and the bottom would be 0. So at this point, I have an indeterminate answer. That means I don't know if there's a limit. I have to do some simplification first. So the limit as h approaches 0. So I think about this one, what would be my most useful strategy? And expanding would be at this point. So I've got 80 subtract 5 times, and I'm going to expand 1 plus h squared would be 1. Outside inside would be 2h plus h squared, subtract 75. And I'm sorry, I was doing multiple steps yesterday and confusing some. We have 80, subtract 5, subtract 10h, subtract 5h squared, subtract 75 over h. Okay, if I have 80, subtract 5, I've got 75. 75, subtract 75, they're gone. I am left with stuff on the top that all has h's in it, so I'm going to factor out an h. So for the two remaining terms, I actually have negative 5h as my greatest common factor, which would be 2 plus h, checking my signs, I'm good, over h. Cool. I see an h in the numerator and an h in the denominator. I can cross those out, and away goes my 0 over 0 problem. So right now, I can put a 0 in for h, and I don't have to write the limit as h approaches 0 again, because I've taken the limit as h approaches 0. So I am left with negative 10 as my instantaneous rate of change when t equals 1. So at that moment, t equals 1, the rate of change is negative 10 meters per second. That makes sense. We know that that velocity is changing as we go down this table. And at this moment, right here, we have an instantaneous rate of change of negative 10. That fits in with the average rate of change we looked at previously. Let's look at a second example in manufacturing. The total cost of manufacturing X units of a product is given by 10 root X plus 100. We know what that looks like from transformational thinking. We have a function that's been moved up a 100. We have a function that has a vertical stretch, factor 10. And we know that it was originally, the parent function was the square root function, so we know that this graph would look like up 100, fairly steep, like that. Okay. So with that in mind, we're going to fill out the table of values, and we're going to determine the rates of change and the instantaneous rate of change. So when my X value is 0, I have produced 0 units. I still have an initial value of 100. If I manufacture 50 units, it gets kind of ugly, so please have your calculator out and check my numbers, but I had 170.7 approximately. If I produce 100, that number's nicer. Square root of 100 is 10. 10 times 10 is 100, plus 100 is 200. 150, 222.5 is my cost. And for 200, also ugly, 241.4. Check my math. Okay. We're going to look at all the intervals separately and see if we can see what's going on. So from 0 to 50, my instantaneous rate of change, my average rate of change in that interval would be a change of 70.7 dollars, whatever it is, dollars, over 50, which would be approximately $1.414 per unit. From 50 to 100 units, the rate of change would be 29.3 in 50, which is approximately $0.586 per unit. So things are changing. In the interval 1 to 150, my change is 22.5 in 50, which is approximately $0.45 per unit. And in the last interval, 150 to 200, I have a change of 18.9. I did that in my head, not a calculator. Oh no. Over 50, which is approximately 0.378. So we see that the difference in the interval is getting smaller and smaller. We're going to look at the instantaneous rate of change at x equals 100. So how is the price changing at exactly that point? Okay, and we'll talk about a little bit more about what that means in a second. I am looking for the limit as h approaches 0 for the function at 100 plus h over h. So that instantaneous rate of change at that point is the limit as h approaches 0 for my function, which is 10 times the root of 100 plus h plus 100. There's my function. Subtract. The function at 100, I already know that because I have that on my table of values. I know that point is 100, 200. So I'm just going to put 200 in here, all over h. If I were to put a 0 in right now, I'd have 0 over 0, so it would not tell me a thing. So I need to keep simplifying. For this one, our strategy is we have roots, and that's a bit of a problem. So I'm going to rationalize this thing to get rid of the root sign and be able to, so my whole goal, by the way, is to try, and we're going to erase this, is to try and isolate h over h so I can cross them off to get rid of the 0 over 0 indeterminate. Okay, that's my goal. I'm going to rationalize this thing, so I got to write a lot smaller than I am right now. Okay, so the top I can just tidy a little bit. I've got 10 root 100 plus h, and I'm going to put that 100 and the negative 200 together. And if I want to rationalize that thing, I'm going to multiply by 10 root 100 plus h plus 100 over 10 root 100 plus h plus 100. So I'm multiplying by 1. Okay, I got to remember where I was. Mrs. Sterling just scared the life out of me. Okay, I'm multiplying by the conjugate, so I can get the h out from under the root sign, so I can cross off the 0 over 0 problem. Okay, here we go. Multiplying by the conjugate is, your thinking is like FOIL. On the top, I just, for sake of visual, I just bracket it and say, oh yeah. I've got firsts, which is 10, 100 times 100 plus h. Outside, inside would cancel. I would have 1,000 root 100 plus h subtract 1,100 plus h. And then last would be negative 10,000. All over ugliness, h times. I'm not even going to tidy that up because I know I'm putting a 0 in there in a bit anyway, so why would I go to the headache? Okay, one more limit as h approaches 0 as we tidy this up. I have 10,000 plus 100h. Subtract 10,000. Oh my goodness, they disappear. Crazy. I am left with 100h on the top. I am left with an h on the bottom. 10 times 100 plus h root plus 100. Okay. I have gotten rid of the 10,000s. I am dividing out an h and an h from top to bottom. I can now do the limit as h approaches 0 by putting a 0 in wherever I see an h. I have 100 on the top. So my 0 out of 0 problem is gone. If I put a 0 under that root sign, I have the root of 100, which is 10. Excellent. Almost done. 100 over 200, which is 1/2. Now we need to think a little bit about what does this mean. It is the cost at that moment to produce one more unit. So that instantaneous rate of change would be the cost to produce the 101st unit. Of whatever it is that we're producing. The average rate of change was that average change in cost over that interval. So the more that we are, as you look at those intervals, the more that you produce, the less the unit cost is, and that makes sense. We kind of absorb that initial cost into our costing, and so the more you do, the less it's going to cost average. All right, you've got some homework to work on.